into pure cognitive espresso shots knowledge that sticks and makes you sound much smarter at the dinner table.
Oh, I like that.
Today, we are undertaking a deep dive into what is probably the single most influential architectural breakthrough in modern AI history.
It really is.
We're talking about the engine that's running literally everything. I mean, from the complex reasoning of LLMs like GPT-4 to these staggering scientific feats like AlphaFold 2's protein structure predictions.
And that engine is the transformer architecture. It's really hard to overstate the magnitude of its arrival back in 2017. It all came from a Google paper that had this bold, almost provocative title.
Attention is all you need.
That's the one.
And that title, it wasn't just catchy, was it? It was a revolution in 4 words. Their mission, which is now our mission for this deep dive, was to show that this concept of attention wasn't just, a feature.
No, not at all. It was the foundational mechanism you needed to build truly scalable AI.
So that's what we're going to do. We're going to extract the core, the intuitive mechanics of this technology, and trace its direct lineage from a theoretical paper to models that are now using, over a trillion parameters?
It's an incredible story. And the intellectual audacity of that paper, it was authored by 8 scientists from Google. It lay right in that core claim. They basically proposed eliminating the sequential data flow that had been the bedrock of AI for decades.
Throwing it out completely.
Throwing it out, daring to rely solely on this attention mechanism. And here's a great piece of trivia that I think shows just how quickly this shifted from a research project to, like, an industry foundation.
Go on.
The name Transformer was actually chosen just because one of the authors, Jacob Tsukright, admitted he just liked the sound of the word.
You're kidding. Something so fundamental named on a whim.
Pretty much. But the consequences are anything but flippant.
No, definitely not. I mean, the sheer impact of this work is measurable. As of 2025, that single paper has been cited over 173,000 times.
Which is just a staggering number.
It places it among the most cited scientific texts of the entire 21st century. It is the undisputed foundational text that didn't just ignite the current AI boom. It provided the technical scaffolding that made large language models, as we know them, physically possible to build.
Couldn't have said it better myself. It was the key that unlocked the whole thing.
So to really grasp why the Transformer was such a seismic shift, we have to look backward. I think we need to understand the agonizing, often insurmountable bottlenecks that define the AI era that came right before it.
Exactly. It's a story of these sequential models just hitting a wall they couldn't climb over no matter how much data or computing power you threw at them.
That's the critical context, isn't it? Before 2017, the deep learning world, it relied so heavily on fixed input sizes for certain tasks.
Right. If you were working in computer vision, you had convolutional neural networks, CNNs, and they were engineered to process a square fixed grid of pixels, say 224 by 224.
Very predictable. Very predictable. But the moment you needed to handle inputs that were inherently variable, like a sentence, a paragraph, a long stretch of DNA, you immediately ran into some really severe limitations.
And for those variable inputs, the standard approach was sequential processing. That's where we get recurrent neural networks, RNNs, and their more robust cousins, the LSTMs.
Right. Long short-term memory networks. And RNNs processed input meticulously, one token or one word at a time. This iterative loop was their defining feature.
So the network's ability to process the current step, which we call step T.
It relied strictly on 2 things: the input token itself and the hidden state that it got from the step right before it, T1. This structure was designed to maintain a short-term context, so the network could remember, for example, the first few words of a sentence.
But standard RNNs were, they were notoriously unreliable for anything beyond really short, simple phrases. That's why LSTMs became the go-to architecture for a long time, right? They seemed like this brilliant, almost desperate improvisation to patch the RNN's memory leaks. They absolutely were an improvisation, and a brilliant one at that. LSTM had introduced this specialized memory structure called the cell state.
Okay, what's that?
Think of the cell state as a continuous internal memory tape. It's capable of carrying relevant data forward across long periods without being constantly overwritten.
Like an information highway.
It's exactly like an information highway. And it uses 3 key instructions: the input gate, the output gate, and most importantly, the forget gate, to selectively regulate what information gets added to or removed from or read out of that internal memory.
So LSTMs dramatically improved context retention for, let's say, moderately long sequences, by mitigating that problem of context decay. They
Yeah.
made the network much more robust.
They did.
But they still couldn't fundamentally eliminate the core constraint of sequential processing, and that is what led to the true scaling crisis.
Precisely. This scaling crisis, as we call it, was driven by two linked, mutually reinforcing flaws, and LSTMs couldn't truly conquer either of them. Let's start with the theoretical one, the most notorious limitation: the vanishing gradient problem.
This is the thing that gave deep learning scientists nightmares for decades.
Oh, it really did. To train any deep network, you need to use a process called backpropagation. In these sequential models, this becomes backpropagation through time, or BPTT.
Okay.
So the network needs to calculate how much each weight contributed to the final error. And this error signal, the gradient, it has to flow backward through every single time step.
So wait, if I have a 200-word paragraph, the correction signal for the very first word has to travel backward through 200 separate computational steps just to get there.
That's exactly right. And here is where the catastrophe lies. At every single one of those steps, that error signal is multiplied by the derivative of the nonlinear activation functions used in the network.
And those derivatives are small numbers.
Almost always small numbers, less than one. So the repeated multiplication of a small number by itself causes the magnitude of the gradient for those early tokens to shrink exponentially fast.
It's the difference between multiplying 0.9 by itself once versus multiplying it by itself 100 times. The final number is basically zero.
It's effectively zero. Conceptually, it's like trying to shout a critical correction to the person standing at the very beginning of a massive queue.
Yeah.
By the time that message passes through 100 people, and each one whispers it a little quieter than the last, the message is just an inaudible whisper by the time it reaches the person it was for.
So the weights for the early words in a long sentence get almost no update signal, making these crucial long-range dependencies, like connecting a subject's 100 words ago to a distant verb, virtually unlearnable.
It was a crisis of information integrity. And even though LSTMs had that clever cell state, that information highway that could try to keep the gradient stable, they still couldn't entirely escape this problem.
But even if they could, the second crisis was purely practical, and maybe even more devastating for scaling. We're talking about the GPU paradox.
This is maybe the most pragmatic and ultimately the most critical insight behind why the Transformer was so successful. By 2017, we had access to incredibly powerful hardware. GPUs,
Right.
graphics processing units, and these things are specialized pieces of equipment. They have hundreds, sometimes thousands, of processing cores. They're designed for one task above all others: massive parallel computation. They thrive on doing thousands of matrix operations simultaneously.
But the architecture of RNNs and LSTMs, their very definition, required them to process the sequence linearly. One step must finish before the next one can even begin.
And that linear step-by-step dependence created a fundamental incompatibility with the GPU architecture. You could train multiple sequences at once in a batch, but the calculation within a single long sequence remained stubbornly sequential.
So most of the GPU's parallel processing power was just sitting there, idle, while a single core waited for the previous step to complete.
Exactly. This inability to leverage GPU parallelism meant that scaling up the model size, or crucially increasing the sequence length, came with this disproportionately astronomical cost in training time.
It sounds like trying to use a drag racer to navigate a crowded city street. The tool is incredibly powerful, but its design is just fundamentally wrong for the task.
That is an excellent analogy. The sequential bottleneck was the scaling impediment that had to be eliminated for AI to progress to the next level.
And that is the radical shift. The Transformers solved both the theoretical crisis of vanishing gradients and the practical crisis of the GPU paradox at the same time, just by eliminating recurrence entirely. It allowed all the tokens to be processed in one massive parallel operation.
So to replace the function of recurrence, which was, providing context, the transformer architecture relies solely on the attention mechanism.
And attention wasn't a brand new idea, right? It had been around for a few years.
Right. It was first introduced back in 2014 as a way to augment RNNs to help them focus.
Yeah.
But the 2017 paper made it the entire foundation, and that was the game changer.
Okay, let's start with a basic definition so you can grasp it immediately.
Yeah.
What is attention at its most intuitive level?
Intuitively, attention is a specialized process we call attention pooling. So imagine you have a vast database of information. Attention pooling is an operation that figures out which pieces of data in that database are most relevant to your current focus.
And then what?
And then it calculates a linear combination, a weighted sum of those relevant pieces. The weights tell you precisely how much attention to pay to certain terms. So the output is this highly focused, weighted average of just the meaningful values, concentrating only on the most relevant context.
So instead of the old way, which was trying to compress a whole sentence into one tiny, overstuffed, hidden state vector, we're now assigning a score to every single piece of information to decide how relevant it is to the current word.
Precisely. And this leads us to the conceptual foundation of the transformer's power, the QKV framework. It stands for queries, keys, and values. And you should think of this not just as abstract math, but as a highly efficient, high-speed, content-addressable memory lookup system. It behaves just like querying a massive database of language.
Okay, let's ground this. Let's use an example. Say we have the sentence, the tired animal rolled and then it slept. When the model gets to the word it, which needs to figure out what it's referring to, how do Q, K, and V operate?
Great example. So in that moment, the current word it generates the query, Q. The query represents the need or the criteria of that current word. It's basically asking the whole sentence, what information from the surrounding context is relevant to define me? It is the search request.
And that query has to be matched against all the available possibilities in the sentence.
Correct. So every other word in the sequence, tired, animal, rolled, slept, each of them generates a key, K. The key represents the index or the inherent properties of that word. You can think of it as a label or a tag that the query tries to match against.
So the query from it is trying to see how well it aligns with the key from animal or the key from rolled.
Exactly. And if the query from it successfully matches the key from animal, that match generates a high attention score. It flags it as highly relevant.
And that score determines how much weight is given to the third part, the value.
Exactly. The value represents the actual rich, embedded numerical meaning, the data payload of all the words. So if the key of animal aligns extremely well with the query of it, the rich contextual value of animal is heavily weighted, it's aggregated, and it gets folded into the final contextual representation of the word it.
That is incredibly clear. It's a dynamic, context-aware memory lookup. But okay, how do we formalize that high-level database idea into matrices that a GPU can actually compute in parallel?
We use linear algebra. The queries, keys, and values are all packaged into dense numerical matrices, Q2 and $5. And the specific mathematical method used is called scaled dot product attention.
Okay, so walk us through how the scoring works in that matrix format.
To score how well the queries match the keys, we perform a massive matrix multiplication. We compute the dot product of the two-up matrix and the transpose of the dollars matrix. We write that as Q catal dollar.
And the dot product is basically just a measure of similarity, right?
It's mathematically equivalent to calculating the similarity between all possible pairs of query and key vectors simultaneously. This gives us a giant matrix of raw affinity scores, telling us which words are paying how much attention to every other word in the sequence.
And this all happens instantly, in parallel, across the entire sequence. No more waiting.
That is a parallelization payoff. But before those raw scores become the final weights, two steps are really critical. And one of them actually addresses a very subtle vanishing gradient problem that the transformer itself creates.
You mean the internal vanishing gradient problem associated with the softmax function?
Precisely. If the dot products between $10 get too large, and they will in high-dimensional space, when you pass them through the softmax function, the resulting probabilities can become extremely sharp. The highest scores become nearly 1, and everything else just drops to basically 0.
They call that saturation, right?
Saturation, yeah. And when the softmax function saturates, the gradients of all the non-chosen paths just vanish, which really hinders the model's ability to learn subtle, complex relationships during training.
Ah, so the original paper explicitly tackles this with the scaling factor.
Yes. The raw dot product result is first scaled down. You divide it by the square root of the key dimension. This step is deceptively important. It keeps the dot products in a manageable numerical range, preventing that saturation. It ensures that the softmax function operates in its most sensitive, nonlinear regime, where the gradients are robust and learning can happen efficiently.
So scaling is essential for stabilizing the learning process. And once it's scaled, you apply the softmax function, which converts those raw scores into easy-to-interpret probabilities that all sum up to 1.
And that softmax output is what we intuitively think of as the mask. It's the exact dynamic set of weights that tells the model where to focus its attention.
And then finally, you multiply that weight mask by the value matrix, V.
Right. And that gives you the final contextualized output vector for the entire sequence. That resulting output vector for our word it is now a perfect weighted blend of the rich meanings of tired and especially animal, all processed simultaneously and completely free from that sequential decay we saw in part one.
The beauty of the QKV mechanism is its flexibility. It's this core computational primitive that you can deploy in different configurations, which leads us to the modular components of the transformer,
Yeah.
the encoder and the decoder.
That flexibility really starts with the distinction between the two types of attention used in the original architecture. So the type we just detailed is called self-attention,
Okay.
and it's primarily used in the encoder stack. This is where Q, K, and V all originate from the same source, the input sequence itself. So it's all about weighing the importance of other words within that context window to maximize the understanding of the current word. It's all about input representation.
And then there's the mechanism that links the two halves of the model, the part that's necessary for a task like, say, language translation.
That's cross-attention, and it's used exclusively in the decoder. So here, the query, the Q, comes from the partially generated output sequence. Let's say the word currently being generated in German,
Right.
but the key and the value, K and V, they're sourced from the output of the encoder, which is the summary of the English input sentence. This forces the generated word to stay grounded and relevant to the meaning of the source sentence. It creates that essential link that maintains coherence across the languages.
Now, if we look at the official architecture diagram from the paper, we don't just see a single attention layer. We see something called multi-head attention. Why the complexity? Why run several copies in parallel instead of just one giant calculation?
Yeah, that's a great question. Think about how complex language is. A single attention score might be robust enough to catch the biggest, most obvious relationship, the subject of a sentence.
But it might miss the subtle stuff.
It might completely miss the subtle or multifaceted relationships. If two different sentences have the exact same words but in a slightly different context, a single attention head might yield similar scores. It fails to capture the nuance.
And this is where that team of experts analogy comes in.
Precisely. Multi-head attention is like convening a team of specialized computational experts. The model runs several parallel copies. The original paper used 8 separate heads of the self-attention mechanism, but here's the key part.
It's that.
Each head has its own distinct, learned set of weight matrices for projecting the input into its own unique Q, K, and V spaces.
So one head might learn to specialize in identifying the subject of the sentence, while another learns to track time relationships, and maybe another one specializes in resolving who it refers to.
That's the intuition exactly. Each head learns a different representation subspace of the input data. By running these varied projections simultaneously, the model captures a much richer, more diverse, and less brittle set of relationships. The outputs from all these heads are then just concatenated back together and linearly combined to form a singular, highly robust final representation that's been looked at from multiple expert angles.
Okay, so we've solved scaling and we've maximized context with QKV. But by eliminating recurrence and convolution, we created a new, pretty fundamental problem. The transformer is inherently permutation invariant.
Meaning it doesn't care about order.
Right, if I feed it dog bites man or man bites dog, the self-attention calculation sees the same set of weighted relationships because it sees them all at once. It has no sense of word order.
And that loss of sequence order is the critical vulnerability that positional encoding had to fix. Since the attention mechanism processes everything in parallel, we need some external injection of information that tells the model the relative or absolute position of each token in the sequence.
And the fix for this was to take the word embeddings, the numerical representation of the words, and simply add a secondary vector, the positional encoding vector, to them right at the start of the stack.
Yes, and the true stroke of genius in the original paper was the design of that positional vector. They didn't just use simple integers like 1, 2, 3, which don't scale well. They used fixed sine and cosine functions of varying frequencies to generate the encodings.
That sounds a little esoteric. Why that specific choice?
It might sound that way, but it was a deliberate, powerful mathematical choice for 3 main reasons.
Okay, what are they?
First, the functions are periodic. This allows the pattern of positional information to repeat across different parts of the sequence, making the relationship between positions generalizable, not unique. Second, they are smooth and continuous functions, which is absolutely essential for stable differentiation and effective optimization during training.
And the third, most future-proof benefit. That ties directly back to scaling and generalization.
That's the one. It's the ability to extrapolate to sequence lengths longer than those encountered during training. Because the position is encoded mathematically as a periodic function, not a memorized lookup, the model can instantly recognize the position of word 10,000, even if it was only ever trained on sentences up to length 5,000. It generalizes the mathematical pattern of position.
So it induces the necessary bias toward input order without restricting future capability.
Exactly.
So with those core components, multi-head attention, cross-attention, and positional coding, we can now assemble the whole machine. The transformer is composed of two primary stacks, the encoder and the decoder.
The encoder stack is devoted entirely to deep understanding and representation. In the original paper, it had 6 identical layers. Each layer contains 2 sublayers, the multi-head self-attention unit, and then a subsequent feed-forward network, or FFN. The encoder operates on the input simultaneously, generating this dense, context-rich, latent representation that summarizes the input's meaning.
And the decoder stack takes that summary and does the generation part.
Right. The decoder, also 6 identical layers, generates the output sequence 1 token at a time. This is called autoregressive generation. It's a bit more complex. It has 3 sublayers.
Okay.
First, it has the specialized mask multi-head self-attention. This masking is paramount for training the generation process. It ensures that when the model is predicting the next word, word I, it can only attend to words that came before it, from 1 up to I1.
So it prevents it from just cheating by looking ahead at the answer.
It can't cheat, exactly. The second sublayer is that cross-attention mechanism we define, which allows the decoder to query and ground its generation in the contextualized output provided by the encoder. And finally, both stacks use a standard feed-forward network, which is applied independently to each position's vector, mapping the complex attention-weighted context into a higher-level feature space.
And supporting this entire deep architecture, making sure training remains stable and fast, are 2 critical but often overlooked stabilization techniques. We should talk about residual connections and layer normalization.
Absolutely vital. Deep networks, those with many, many layers, face this challenge of information degradation. As information flows through dozens of transformations, the initial information can start to wash out or get lost. This also makes backpropagation unstable.
So how does the residual connection solve this?
The residual connection introduces a simple but really profound idea. You take the input to a layer, you calculate the layer's output, and then you simply add the original input back to the layer's output. It's written as $6 plus text from sublayer.
So it creates a shortcut path.
It creates a direct shortcut path, a residual path for the information, and critically for the gradient to skip over complex transformations. So instead of forcing the network to learn the entire complex function from scratch in every layer, it only has to learn the difference, or the residue, between the input and the ideal output.
Which stabilizes and dramatically speeds up training. And the second technique, layer normalization.
Layer normalization addresses internal instability. Now, normalization is a common technique, but unlike batch normalization, which normalizes features across an entire batch of inputs,
Right.
layer normalization normalizes the feature vectors within each individual input sample.
And why is that better for something like language?
Because the length of the input sequence varies wildly. Batch normalization performs really poorly when the input sequence length is unpredictable or when your batch sizes are small. Layer normalization provides consistent statistics regardless of the input length, which is fundamental for dealing with language, where one sentence might be 10 words and the next might be 50. These 2 elements, residual connections and layer normalization, were absolutely vital to making sure that training these deep transformer stacks was a tractable, stable process.
So the moment the transformer was formalized and stabilized, the scaling of AI models went from, linear growth to a truly exponential explosion. We went from being theoretically limited by sequence length to being practically limited only by how much money and hardware you could throw at the problem.
This is the massive parallelization payoff in action. The transformer's inherent design finally allowed developers to fully utilize the parallel computational power of the GPU architecture. This acceleration meant that training times for massive data sets just plummeted.
Which in turn allowed researchers to reallocate resources to vastly increase the number of model parameters without incurring those crippling time costs.
Exactly.
So let's put this parameter explosion into raw numbers, because the progression over just a few years is staggering. It really helps you appreciate the change in capability.
Oh, it really is staggering. The pre-transformer LSTMs, they struggled to break 100 million parameters. When the first large transformer models arrived, the encoder-only architecture called BERT in 2018. They came in a couple of sizes. BERT Large had 340 million parameter.
And that was considered huge at the time.
It was absolutely massive, but the architecture was so efficient that just 2 years later, we saw a leap into the billions.
We're talking about GPT-3.
Correct. GPT-3, a decoder-only model, arrived in 2020 and jumped to an astonishing 175 billion parameters. And then you fast forward to the state-of-the-art systems today. GPT-4, released in 2023, is widely estimated to have roughly 1.8 trillion parameters.
That is a number that is just hard to grasp. From 340 million in 2018 to 1.8 trillion parameters in less than 6 years.
It represents a staggering 10,000-fold increase in scale from those early large transformer models. This exponential scaling, fueled by the parallelization efficiency of the attention mechanism, is the direct empirical cause of the dramatic advancements in linguistic fluency, context retention, and reasoning capabilities we're seeing in these modern foundation models.
But, using a full 1.8 trillion parameters for every single query, that sounds astronomically expensive, both in energy and in time. If scale is the answer, efficiency must have been the next big challenge. Did they find an architectural trick to manage that trillion parameter cost?
They absolutely did. And this breakthrough is key to the efficiency of models like GPT-4. It's the mixture of experts architecture, or MoE. It's really the next evolution of the transformer. The estimate suggests GPT-4 uses a collective of 8 different models, or experts, each made up of about 220 billion parameters, which totals up to that 1.76 trillion we often cite.
So it's not one massive single brain. It's more like a team of specialized subbrains that can be called upon as needed.
That's the perfect intuition. In a traditional dense transformer like GPT-3, every single one of those 175 billion parameters is activated and contributes to the computation for every token.
Every time.
Every single time. In a MoE architecture, only a tiny fraction of the parameters is active for any given request.
So how does the system know which expert to call on for a specific task?
That routing decision is handled by a specialized component called the gating network, or the router. It's a small, separate neural network that learns, during training, to assess the input token and determine which one or two experts are most relevant for processing it. So, for example, if the input is a complex physics problem, the gating network might route it to the physics expert and maybe the mathematics expert.
That sounds like a revolutionary efficiency trick.
It is. It means that while the model has the collective power of 1.8 trillion parameters, only, say, 110 billion parameters might be actively used for a specific conversation. This dramatically reduces the cost per inference and the latency, the speed of the model, compared to a truly dense transformer of the same size. It's how these companies maintain capability while keeping their operating expenses manageable.
And beyond sheer size, that scaling unlocked these fundamental functional advancements we now just take for granted, starting with memory, or the context window.
Oh, the context window is a huge one. It's the model's ability to remember and attend to relevant information during a conversation. GPT-3's context window was painfully limited to 2048 tokens.
Which is about 1,500 words. Not much.
Not much at all.
Yeah.
If you had a slightly longer conversation, the model would literally forget what you said a few turns ago. GPT-4 drastically increased that capacity to 128,000 tokens.
That's a staggering increase in memory. It lets it analyze vast documents or maintain coherent, multi-hour conversations.
Absolutely. And the scaling also seems to have unlocked something even more profound, actual improvements in reasoning. Older models would often just flail on complex, multi-step problems.
Right.
Newer models, like the Advanced O1 series researchers have mentioned, they aim to explicitly improve reasoning by introducing a form of internal monologue.
So they don't just spit out the final answer.
No, they're trained to think through the problem step by step internally before generating the final answer. They generate a chain of thoughts or intermediate steps, which significantly improves precision and reliability for non-trivial tasks, like coding, mathematics, or complex logical puzzles. The scale allowed them to learn not just what the answer is, but how to arrive at it.
And finally, I think the ultimate proof of the Transformers architecture wasn't just in text generation, but in its swift expansion into multimodality.
The transformer proved it could handle sequences of any kind of data. Initially, models like GPT-3 were text-only, unimodal. GPT-4 introduced the ability to process text and static images. But the most recent iteration, GPT-4o, where the O stands for Omni, advanced this even further. It can process and generate highly synchronous and continuous sequences of text, audio, image, and even video formats. The architecture generalized across sensory input types almost instantly.
The journey of the transformer from an NLP mechanism to this universal architecture. It's the definitive proof of its power. It generalized so successfully, far beyond its birthplace, confirming its ability to process any form of structured, sequential data.
The first major leap outside of natural language processing was into computer vision, which resulted in the vision transformer, or VIT. And for years, images were entirely the domain of convolutional neural networks, CNNs, which had a very local, pixel-focused approach.
So how did the transformer, which was built for words, conquer images? It seems like such a different problem.
The core insight was actually pretty simple. Treat the image like a sentence. VIT decomposes a static image into a sequence of fixed-size, non-overlapping patches.
Like little square tokens.
Exactly, typically 16 by 16 pixels. These patches are then flattened and treated exactly as if they were words in a sentence.
So you take a high-resolution photograph, you chop it up into a big grid of squares, and then you just feed that linear sequence of squares into the transformer's encoder stack.
Precisely. You apply positional encoding to these patches so the model knows the spatial location of each square within the original image. And then the multi-head self-attention mechanism computes relationships between every distant patch. This allows the model to capture global dependencies, how a region in the top left relates to a region in the bottom right across the entire image instantly.
Instead of the localized hierarchical pixel patterns that CNNs focused on through their receptive fields.
Exactly. And the results weren't just competitive with CNNs, they were revolutionary in terms of resource efficiency, especially at scale.
How so?
They were stunning. When trained on truly massive datasets, and we're talking over 14 million images, VIT models achieved state-of-the-art accuracy while requiring up to 4 times fewer computational resources for pre-training than the best-performing CNNs. This efficiency proved that the transformer was a superior scaling engine for vision as well.
That begs the question, though. If VITs are so efficient and effective at scale, why would any computer vision engineer still use a CNN?
That comes down to something called the inductive bias trade-off. A CNN is built with certain image-specific biases hardwired into its architecture. The way convolution works naturally assumes local spatial correlations, which is a great prior for images.
But VITs don't have that.
VITs lack those hard-coded biases. This means that while they can learn incredible generalization when given massive amounts of data, they're far less data efficient than CNNs on smaller, more constrained training sets. Their superior performance hinges entirely on that availability of sheer data scale.
If the leap into vision was a major technological step, then the application in scientific discovery feels like a shift in human capability. I'm referring, of course, to DeepMind's AlphaFold 2.
The protein folding grand challenge.
Which it solved.
It did. And AlphaFold 2's success is a landmark validation of the transformer's core strength. Protein folding is a decades-old problem that is fundamentally a long-range dependency challenge. A protein is assembled as a simple 1D sequence of amino acids, but its final functional 3D structure is determined by these complex interactions, where amino acids that are far apart in the 1D sequence end up being physically next to each other in the folded 3D structure.
So the challenge is mapping a relationship across vast, non-adjacent distances in the input sequence to a geometric truth in 3D space.
Exactly. And since the transformer, via attention, is uniquely designed to find and compute those long-range dependencies instantly and in parallel relating every amino acid to every other amino acid simultaneously, it was the perfect architectural fit. AlphaFold 2 used a spiralized version of the attention mechanism to model the geometric distance matrix of amino acids in 3D space.
Which is the core of the folding problem.
It's the core of the problem. The global context provided by attention was ideally suited to solving that non-local constraint, enabling this transformative breakthrough in computational biology that promises to reshape drug discovery and basic science.
It's just astonishing, whether it's predicting the next word in a complex conversation, identifying objects in a high-resolution video, or predicting how a complex synthetic protein will fold. The transformer is now the universal meta-architecture for identifying these high-value contextual relationships in virtually any structured data.
So what we've distilled today is this simple yet radical intellectual move that really launched the current era of artificial intelligence. It was a technical necessity, and it was driven by hardware limits.
We've seen how the idea of replacing slow sequential processing with parallel attention, defined by that elegant and scalable query, key, and value lookup system, simultaneously solved the theoretical crisis of the vanishing gradient problem and eliminated the sequential bottleneck that kept our powerful GPUs sitting idle,
And that shift is what unlocked the age of exponential scaling.
moving from struggling with hundreds of millions of parameters to efficiently managing a trillion parameters in less than a decade.
The architecture then confirmed its universality by successfully migrating from text to images with VIT and into fundamental scientific fields like biology with AlphaFold 2. The transformer is, without a doubt, the foundational technical breakthrough of the 21st century's first decades.
However, despite this monumental success and the exponential growth it enabled, the canonical self-attention mechanism still faces one major looming hurdle, and it's one that defines the future limits of AI, memory, and scale.
That hurdle is defined by its computational complexity. The original self-attention calculation requires computational complexity that is quadratic. It's mathematically expressed as 1 into dollar with respect to the sequence length, n.
Okay, let's break down what dollars means for you, the listener. Quadratic scaling means that if you're processing a document and you decide to double the length of that document, the amount of computation and memory required doesn't just double, it quadruples.
Right. And if you increase the sequence length by a factor of 10, the computational cost increases by a factor of 100.
100 times more.
Precisely. That $2 growth is why context windows, even at 128,000 tokens, still feel limited when you want the AI to analyze an entire library of multi-volume textbooks or maintain a continuous year-long memory of your interactions. The memory and compute costs associated with longer sequences quickly become economically and physically intractable because of this quadratic relationship.
So the transformer solved the scaling problem that plagued RNNs, but it inherently introduced its own much higher scaling limit.
And that quadratic scaling is the absolute boundary currently limiting future AI memory and the ability to process truly long-form context. Therefore, the provocative thought we want to leave you with is this. Despite having achieved trillion-parameter models, the next truly radical architectural breakthrough in AI may not come from adding more parameters,
Well, from where?
but from developing more efficient attention variants. Innovations aimed at finding a clever mathematical way to make attention's complexity linear, so nearly linear, rather than quadratic. Managing the memory and compute costs necessary to finally build AI systems capable of truly boundless long-term memory.